I'd like to kick off the start of the second part of the tissue activation session. There's one thing which I should have said at the beginning of the last session, which I forgot, and that is that if you're a speaker and you're asked a question, if you could please repeat the question so that people at the back can hear, because I know it is quite difficult to hear somebody at the front asking a question. So speakers, I'll probably forget to remind you individually, but if you could try and remember to repeat the questions back so everybody can hear, that would be very helpful. So we're going to start this next session with Sasha Panfilov, who's going to be talking about electrophysiological metrics and geometry of the heart.
Thanks a lot for invitation. I would like to report on some new line of research which we started already maybe a few years ago, and it's a bit more mathematical, and I think it would be a good place to talk about this, and this is a joint work with HS France, with Robert Young, and it deals with some geometrical interpretation of anisotropy of the heart. What we know about anisotropy of the heart? The most detailed model of anisotropy of the heart is a tropic model proposed in Auckland, which uses three main directions: along fibers, along myocardial sheaths, and across fibers. And this structural heterogeneity naturally implies autotropy with electrical wave propagation, and this was very recently measured in experiment in Bruce Smith's group, who showed that there is indeed a difference in velocities of propagation in these three directions, ranging from, for example, 1 to 1/2 to 1/4. When we talk from geometrical point of view, then anisotropy is nothing else than rescaling. Indeed, if you take just a circle and compress it, for example, 2 times along this axis, you will get an ellipse, and this ellipse is exactly what you get in 1:2 anisotropy after initiation of point stimulus and wave propagation here. And basically, people who do simulations know about this, I think, already for quite a while. And I remember even when I was a student, when it was necessary, for example, to get a spiral wave with 1:2 or 1:3 anisotropy, all what you need to do is just to take isotropic case and just compress it in one direction, and you will get a result. And I would say that this is not an approximation. This is exactly what you get if you will solve also your equations in continuous limit in terms of anisotropic medium. Okay, so how can we put it mathematically? One way of doing this is introduction of so-called arrival time space, or L space. So what we will do in this space, we will measure distance between 2 points, not as distance in terms of in centimeters, but in milliseconds, as travel time of wave from point A to point B. And then it is easy to see that this space will give you exactly this rescaling what you want. If, for example, this shows an isotropic simulation and these points after 10 milliseconds of wave propagation, in terms of distance, in terms of electrical distance, they are all 10 milliseconds away from the initiation point, and therefore we get a circular shape in this space. However, of course, we need to pay for this, now distances in this space cannot be measured using simple Pythagorean theorem, and we need to use something more difficult, which involves so-called metric tensor of this coordinate system, which of course is closely related to anisotropy. This arrival time space was used in our PRL 2004 paper, but actually it was nothing else than interpretation of so-called D-1 space, which was introduced by Marcel Wellner in order to study dynamics of stationary shapes of filaments in anisotropic cardiac tissue. And it was a conjecture, and by the way, this principle was later proven in work by Verscheld, Dirks, and Bernos 2007. But what we did in our paper, we just showed that this abstract space, which was used for filaments, actually is nothing else than a space of arrival time of wave. And therefore, it can be used not only for filaments, but for waves as well. Okay, so therefore, we can consider this cardiac anisotropy as some kind of metric space, Riemannian metric. And then there is a question, how we can characterize it? What can we do with that? So the first thing, let us to look to this locally then, of course, when we look locally to space or to anisotropy, of course, the most important is anisotropy. But there are also some not so obvious effects which are related to curvature. We know, of course, that curvature of wavefront is important determinant, and for example, convex front propagates slower than plane fronts, and it may have important influence, for example, for dynamic of reentrant patterns in the house. But what I talk here about curvature of space itself. Here it is a cartoon in two-dimensional space that surfaces may have, for example, positive and negative curvature. And what does it mean? That in positive curvature, geodesics on average converge, which means that, for example, line of currents on average converge. While in negatively curved space, they diverge. Another property is the following. So if you just take a circle, and you can see the about area which is inside this circle, then when you take the circle of the same radius in negatively curved space, then area will be larger than that on a plane. And in positively curved space, it will be smaller. What do we have in reality? So this is a classical type of cardiac anisotropy, is rotational anisotropy. And for this case, it's possible to get this formula for curvature. And what does it show? So it shows two things. So first of all, it shows that rotational anisotropy will induce the negative curvature of the space, so that the curvature is negative. What does it mean? As I told you, negative curvature means that this front expands faster. Therefore, indeed, it shows us that rotational anisotropy makes propagation more effective, and we have even some measure for them in terms of curvature. However, of course, because of these lines diverge, we have a less density of current, and it may have another effect. It may have additional electrotonic load on wavefront propagation. And what are numbers here? If we substitute numbers, for example, similar to those which obtained in Bruce Smale's work, then we will get the radius of curvature of about 1.7 millimeters. Is it large or not? For example, a critical curvature of a front which blocks and cannot propagate was measured in several experiments, and depending on frequency, it ranges between 0.2 and 1.3 millimeters. Therefore, although this curvature is above this, it's pretty much in a range, and we can expect that this curvature may have substantial effect also on wave propagation. And by the way, effect of curvature on propagation was also recently studied by Hans Dirks, and there is a poster about this in poster session. Okay, now let's go to global geometry. For global geometry, Robert Young proved a theorem, and this theorem basically means the following. So if you take we found that our space in which generated by this anisotropy is pretty curved, it's pretty complex space. But if we now consider its geometry at long distances, then it turns out to be Euclidean space and very simple space, in that sense that wave propagation there will be isotropic, and velocity will be close to the maximal velocity possible in this medium, so velocity of propagation along the fiber. In more detail, so if the total rotation is more than 180 degrees, then this result is exact. However, if rotation is less than 180 degrees, then typical shapes will be given by convex hull of individual ellipses in each area, which are shown here, which basically means that 180 degrees, theoretically, we will get isotropic propagation at long distances, and if it is less, then it's pretty much close to it. What is in reality? So this shows some simulations with 180 degrees rotation, and we see circular shapes. If we go to transmural sections, then we see that wavefronts pretty fast establish to some stationary shapes, and indeed start propagate with a constant velocity, and these velocities indeed will be close to the maximum velocity here, which is about 1 meter per second. For 120 degrees of rotation, we still have pretty fast propagation in most of the directions. In some directions it is a little bit slower, but it's still pretty fast. And of course, this slab is a very simple, again, type of anisotropy. And what we did further, we decided to study it in more realistic anisotropic case. And we did not want to go to some fitted model. We wanted to go to raw data. And then we just downloaded a couple data sets from Johns Hopkins University and segmented hard shapes together with anisotropy and set up a simulation. And for that, again, just technical details, we use so-called fast merchant algorithm, which allows to compute like front propagation very fast, and it like does exactly what we need. This distances what we're after, and this shows a typical example of one of simulations. Here just initial simulation point and this propagation of wave. And now let me show what happens in different sections here. So we see that isochrons here, although they do not attain a pretty stationary shape, if you see, like here I show 9 slides from 10, in most of these directions the average velocity of propagation is indeed very, very high. So maximum velocity here is about 1 meter per second, and like in 7 slides, or like 6 slides, it's pretty close to this value. However, there are some slides where it is a little bit slower. This graph shows the overall pattern, and what we did here, we just took 30,000 pairs of points which are spread through all the heart, and we just measured like not only physical distance between these points by initiating wave in isotropic model, but also this propagation in terms of anisotropy, and plotted it against the spatial scale, and size of this box shows how many points relatively from this 30,000 appear in each of this category. And what we see here that indeed when the distance between these 2 points becomes longer, we clearly see that this distance becomes closer, or velocity of propagation increases, and especially at longer distances we indeed see pretty high velocities. Okay, so this is kind of was pretty much an expected for me result, that at large distances isotropic propagation may be a fair approximation of wave patterns. And again, I mean, just personally, many of you know, for example, that many years ago, I mean, Craig Henriquez proposed atrial model, and this model was isotropic, and I thought, why they can do it? But I mean, but basically, it shows that at least in some cases, due to this averaging effect of anisotropy, we can consider propagation is isotropic. But of course, there is one very important feature for global propagation which is missed here, and this is a Purkinje system. And of course, Purkinje system apparently plays a global role for this global for this global excitation patterns. And this is what we're doing right now. We want to extend this research also to include this Purkinje system. It involves some, I mean, experimental work together with some modeling studies and some fitting studies, and I hope to present it later. But now I just want to make simple conclusions that cardiac anisotropy can be considered as geometry, and rotational anisotropy makes propagation faster. And what is interesting, that it indeed, in many cases, goes up to the fastest velocity which is possible here. And finally, maybe one of initial guesses that one of the minimal models of the heart may include isotropic heart with some presentation of Purkinje network. Okay, finally, I would like to thank Misha Gromov for like many valuable discussions, and for many bright ideas which many of those we still were not able to put to our numerical simulations yet, and also James Simons for financial support of this work. Okay?
So actually, I didn't understand that. So in your measure, in your whole heart, you measure conduction delays, and it turned out that your conduction velocity was 0.93 meter per second. Also in your model, how can it be faster than 0.7 meter per second, which was your model parameter?
No. I mean, yeah. So why in our model I show velocity is 0.9 meters per second, but in previous slide it was 0.7 meters per second. Okay. I mean, this is just two different computations. So I mean, for curvature, I showed this with these values of 0.7, but most of simulations in SLAT and in whole heart was scaled to 1 meter per second. So it's not faster than LNF fibers.
Okay.